this video, we are going to explore what is meant by dipole antenna, how the radiation pattern from the dipole antenna looks like, how is the current and voltage distribution in dipole antenna is. Let's see. Dipole antenna consists of two straight collinear conductive elements which is fed at the center. The length of the dipole antenna is half the wavelength, and we are feeding this dipole antenna with an alternating signal. So when this antenna is excited during the positive cycle, the fields on this rod will be like this. That is, this end will be excited and it will be charged plus, and other end will be charged negative. During the next half cycle, it will be reversed. So this end will be charged negative and this end will be charged positive. As these two ends are excited with opposing charges, that is two different electric charges, that is positive and negative, this is known as the dipoles. That's how the name came as the dipole antenna. We said that the length of the dipole antenna is half wavelength, but usually when we are designing, we can reduce the length. Let's see how it is happening. So this is the field distribution in a dipole antenna. Here you can see that the fields are extending beyond the length of the antenna. Due to this effect, that is the fringing effect, we can see that the total effective length of the antenna is increased. So if we are designing the antenna as the half wavelength, the effective length will be more than that. So if we have to design a half wavelength antenna, we can in effect reduce the length. Due to this fringing field, the total length will be ineffective, the half wavelength. So let's see how much reduction in length can be afforded for the dipole antenna design. So it is typically calculated based on the velocity factor. So velocity factor is the ratio of the speed of the wave inside this conductor to that of the free space speed. So in case of a copper wire, the velocity factor is taken as 0.95. What does indicate it is the speed of the light inside the copper conductor is 95% of the speed of the light. That is how the velocity factor is defined. So if we want to design a dipole antenna with copper, we can in effect take the length of the antenna as 0.95 into lambda by 2. So in effect, we are reducing the length of the antenna, and due to the fringing effect, we will be getting an effective length of half wavelength. That's how we are designing a dipole antenna. This is the current distribution in dipole antennas. Here you can see that most of the current is concentrating in the midpoints, and at the edges there are no current at all. Here also these are two representation of the current distribution in antennas using the contours and using the arrows. Here also you can see that most of the current are concentrated in the mid, and at the ends there is no current. So this will be the current distribution in a dipole antenna. Similarly, if we observe the voltage distribution, here we can see that most of the voltage is concentrated at the ends, and at the middle there is the voltage concentration is null. So this is the voltage concentration in dipole antennas. That is, most of it is concentrated at the ends, and in the middle there is nothing. This is the radiation pattern of dipole antenna. It will look like a donut shape, and it is like as a donut is inserted on this dipole antenna. So this donut shape pattern is known as omnidirectional pattern. Here we can see that it has more coverage in the horizontal direction, and in the vertical direction there is no coverage areas. So if we cut this radiation pattern along this red plane, we will be getting a pattern of 8. And if we cut this pattern along this blue plane, we will be getting a circle. So this is the dipole antenna radiation pattern, which is omnidirectional. These graphics shows how the electric fields distributions are happening in different cut planes. So here you can see that along the red cut plane, the electric field distribution happening like this. So this is the only plane where the electric field is transmitting, and this is the plane along the blue line. Here you can see that there is this is the pattern of the electric field distribution. So this is the plane where actually the electric fields are uh, transmitting. So these are some of the dipole antenna parameters. So the total electric field is given by the expression minus lambda by 4 to lambda by 4 d e theta, considering the dipole as an array of infinitesimal Hertzian dipoles. So it is given by this expression, and the total radiated power is based on this electric field distribution and the magnetic field distribution, and the total radiation resistance is related to the total radiated power, and based on the calculation it is approximately 73 ohm. So we have to keep in mind this one, the what is the radiation resistance of the dipole antenna. So this will be very useful in uh, designing the dipole antennas and simulating that in CST or HFSS. We have to use this uh, resistance for the simulation parameters. The dipole antennas are usually narrow band in nature, and one of the technique to increase the bandwidth is increase the radius of the conducting wires. So here is a comparison of the response of the dipole antenna with the two radius 2.5 mm and 5 mm. Here you can see that with increased radius, that is the 5 mm, there is a slight increase in the bandwidth of the antenna. But there are some other issue also when we increase the thickness of these conducting wires. So these are the fringing fields produced from 2.5 mm conducting wire and 5 mm conducting wire. Here you can see that the fringing field produced by the 2.5 mm conducting wire is more, and which will cause effective increase in the length of the antenna. So as the length of the antenna increase, the resonance frequency will decrease. That is why we are seeing the resonance frequency of 5 mm antenna is getting reduced when we increase the thickness. Also, when we increase the thickness, it will be very complex to provide feed in between these two poles. So there are, like, it is like more complexity when we increase the thickness of the conducting wires. I hope you get some idea about what are the dipole antennas and what are its characteristics. So in our next video, we can see how we can simulate the dipole antenna using the CST and how we can see these electric field distributions. Thank you.